Good morning, everyone. How are we all going? Just making sure I've made some settings changes on my streaming software because the last couple of lectures I was getting some crashes happening near the end of the time. So just making sure everything's okay. It seems to be, just looking at all of my stuff over here, seems to be streaming okay. Let me know if anything goes weird. Hopefully the it's a lot of stuff with like the screen resolution and the video streaming, so hopefully there's no problems there and we're all okay. Yeah. People are saying the audio is good, which is good. Someone's saying they're tired. Yes, I do fully understand that week 8 is a tired time where we're all pushing through to the end of term. I sent out a notice yesterday. I didn't send out the usual notice on Monday because I wasn't even in Sydney on Monday, actually. I was actually taking a long weekend. But the second assignment has been released. There's a couple of things I was wanting to talk about. The second assignment has been released. So the core section of the second assignment is available now to do. As far as I remember, the auto tests are now up and running. They're either going to be up and running today or they're up and running yesterday. So pretty soon. And like the version of the assignment, because we released a draft version I think on Sunday or Monday, and then we had a quick look and finalized it, and now the version that's up there now is the one they're actually going to be working on. We've also been given the time for our exam. It's very awkward. It's awkward for us as well because we have to work on the weekend for the exam, which is going to be on Saturday, if I remember correctly. It's the 1st of May, I think. So, you know, it's not ideal, and I know it's not ideal for this to be a Saturday exam, but we put some queries in about the scheduling of the exam, but basically I think with just the sheer number of subjects and the number of people in subjects at UNSW at the moment, weekend exams are happening, which I know is not amazing, but I think it's a matter of it being, if you're trying to squeeze thousands of students together into like a 2-week exam period, some people are going to end up having to be on the weekends, and it's sort of going to be a luck of the draw of how often you're going to end up with weekend exams. Hopefully most of the time you won't have to do weekend exams, but this time for 1511, unfortunately we have to do the weekend exam. At least it's a take-home exam. I will tell you more. I actually have a whole lecture on the exam structure and format, which will be in week 10, so I don't want to go into it too much right now, but you don't have to come into UNSW to do the exam. I mean, many of you are not even able to get to Sydney at the moment because we've still got a whole lot of closed borders around the world due to COVID-19, so the exam will be basically done on your own computer at home, and it'll actually be quite similar to doing things like lab exercises or your assignment and things like that, where you will do some questions we give you and then submit them to us, and then we do the testing and things on our end. Someone said it's right after the maths exam. Is that's kind of awkward because that's like, is that probably 2 really big core subjects happening at the same, like one day after the other? At least you know you're all in the same boat. So all of your marks are going to, like nearly everyone is doing the same 2 subjects. All your marks will drop the same amount, and then us as the lecturers will have to be like, oh, look at that, the whole course has dropped like a 5% average. Maybe we bump it up or something. It depends on the situation. Someone said the exam timetable still says we have to consult the school for times. Yes. So we're running the exam ourselves rather than it being a central UNSW run exam, which means that we will let you know exactly when in the day it is. Last term we ran, I think, Sydney time 1 p.m. to 7 p.m. I think it was a 6-hour thing, but I'm not making any promises about that yet because we've just shifted an hour for daylight savings. What we usually do is we figure out when the time zone works for all our international students and set it at a good time like that. But we haven't done that organization yet, so I'm not going to say anything about how long the exam is or exactly when it is, but we've set it up as an afternoon exam, so it's going to be sometime in the second half of the day. Cameron asked, is it a 2-hour exam? No, it is not. It's much longer than 2 hours. As much as like it is possible to finish the exam in a short amount of time, we give people longer because we can't guarantee that there won't be technical difficulties and stuff like that, so we tend to put like a big buffer time on the exam so that if anyone's computer crashes or something like that, and any of those things that might happen, if it was happening in our computer labs, if we ran the exam in our computer labs and someone's computer crashes, we note down that person, we give them like 15 minutes extra at the end, that kind of thing. But since we can't do that, we just basically do a big buffer so the exam can just go for longer, and if anyone has any hardware issues and stuff like that, it's all sort of built in to what the extra time is the exam gives you. So, I'm not going to say anything more about the exam. We're going to cover a lot of lecture time on the exam later. So I will, I'll talk about that when we actually finalize stuff. So it's not really worth me talking about it now, other than we know exactly which day it's on. So if I remember correctly, 1st of May. I know it was a 5 and a 1 in the date, so I assume it's 1st of May. If it's the 5th of January, that will be very weird, and you'll have forgotten most everything by then. But anyway, let's go into what we're talking about today, because we have work we want to do today, and I've got time dedicated to the exam later. So, what did we learn last week? Hope everyone had some time off over the long weekend, but I hope also that you haven't necessarily forgotten everything that we were talking about last week. So we piled on a few topics last time, but they're all kind of linked together, which is the structs and memory allocation we were working on, which was our ability to create custom variables made up of other variable types. So it's kind of like a container for other variables. I use the bento box example. It's like a lunchbox that has little different sections in it for different types of food. So as opposed to something like an array, which only stores one type of a variable, the struct can store custom amounts of other types of variables, and can even store stuff like arrays as well. So it's kind of like an umbrella container that can contain other variables. And we saw how useful that could be if I just jump down here to linked lists, where if I made a struct and I had it carry a pointer to its own type, then we ended up with the capability of joining these structs together, and we thought of them as nodes in a list. We also had a quick look at multiple file projects. So we did a very, very quick demo of how you link together an H file and a C file and a main file. And we kind of looked at how our single file projects up until this point were kind of like this already. They had a header at the top which had stuff like function declarations and things like that. We had our main, which is just the body of the main function, but then we also had below the main function all of the other actual code for the functions. And if we split those three sections apart into three different files, that's kind of what our multi-file project is. So it's kind of like we were working with all these concepts already, but once we start to organize them, it gets easier to read what we're doing, and it gets easier to organize and separate our data in a sense. So questions. I should not have said stuff about the exam. I was I think Michael will have to answer all the questions about the the exam that are coming up, but don't worry, like there's not that much information there. Ziggy, that is very, very mean. Someone asking what people got in the midterm exam last week. That was an April Fool's joke for last week, so it's only if you happen to be here on April 1st. I made a joke that there was a midterm exam, and like I made it really, really harsh as well. I made it like, oh, it's coming out this afternoon and it's due tonight. So that was just a joke, don't worry about it. I laughed a lot, but that's the most dislikes that I've gotten on a lecture before, so I thought it was pretty funny. Okay, so talking about what we did last week. So structs, memory allocation, we had a quick look at multiple file projects, and then we started building linked lists. The other thing I think that will be interesting to look at is checking out the assignment files, because the assignments are a pre-made multi-file project. And I was talking about the difference between working on, say, the main in a project and working on a C file in a project, where neither one necessarily knows what the other one's doing, but in between the two sits an H file that is what we call an interface, and that defines what both of them should be doing in a sense. In the assignment, you will be just implementing functions in the C file, and those functions will be defined in advance as having very, very specific inputs and outputs, as well as specific purposes that they're supposed to be doing. So you'll get a glimpse at what it's like to actually work in a group where someone else is working on the main files, and you can look in the main files and see what they do, but you don't actually have to use them. So for the moment, we've just got 3 files, which is good. So it's the same kind of setup as that the Batman example that I did previously. But if you get into the extension and you want to do more, we're going to release more files, and you'll see other ways of connecting together multi-file projects. Okay, so what are we doing today? So last week we started working on linked lists, and we were doing the Battle Royale example that I was working on, where I think where we got up to last time was we were able to just build a list of players and print it out, which is a good start, because what we really want to do at the beginning is just get the grasp of what linked lists do. But today we're going to be continuing on that by adding more parts to this project. I was actually thinking about splitting this up into a multi-file project at this point. Especially because we've already done stuff like a type def and stuff, so we might actually do that. I don't know if I'm going to eat up too much time by doing that, but we'll see. So we were building a list, and we were able to loop through it to print it out. So today what we're going to do is we're going to look at adding to linked lists. So we're going to look at the theory behind, if we have an array and we try to insert something in the middle of the array, we have a really weird issue, because there's no space in between elements in an array. So if I want to insert something, I'd have to grab everything in the array, shift it along, and then insert something, which involves looping through and copy and pasting all the way through, that kind of thing. So it's a bit awkward, but a linked list can just shift a few pointers around and insert something. I will draw some pictures and show some pictures and stuff like that for this, because personally I think it's much easier to think about the theory of linked lists visually. You still do need to do the code though, so you still need to translate into code, and a whole lot of this is about understanding how moving pointers works. So if I want to change where a pointer is aiming, then what I'm going to do is change the address that it stores. So it's a combination of knowing that we can assign values to variables, and assigning a value to a pointer is changing where it's aiming. But we'll do all this visually as we're going through it. So, quick recap. What is it? Linked list. Sorry, I just love this guy. It's so funny. I wanted to at some point pick up a leopard print suit and stuff and do a cosplay of Pineapple Pen Man. So, a recap of what linked lists are. This is the key struct that gets us the linked list. The important point is a pointer to its own type, which allows us to link them together in a chain. We can also carry some information, and depending on what we want to do, we'll carry more or less information. So if you've had a look at the second assignment, you'll notice that we're building music in the second assignment, in a sense. Like it's kind of you can't quite hear it, although there is a program that lets you hear some of it. But it's the ability to chain notes together in a linked list. So what we have here is just an integer for data, but even in our example for Battle Royale, we got strings in here, and this struct is not limited to carrying only one piece of information. You can put many variables in there. Oh, people are reminding me how old my meme is. Yes. Pineapple Pen is, I guess, a dated meme now, but he's just so funny. I can't let him go. All right. So visually, this is what we're getting at when we see a linked list. So every node in the linked list is contained in its own piece of memory. So every struct is its own piece of memory. It's not necessarily connected to any of the others. But every node in the list has a pointer in it, which stores the address of the node that comes after it in the list. So this next pointer stores the address where this piece of memory starts. And when we're thinking about it visually, whenever we make a pointer in something, we usually just draw an arrow to wherever it's aiming at. So this node knows that there's another node, and that each of them carries some information. So if it's just an integer, yeah, it's data, but could be strings, could be arrays of things, could be a whole lot of stuff. Could even have other pointers to other things, you know. So there's no real limitation on what you can store in a struct. I guess the only limitation is the soft limitation, which is the meat brain limitation of how much you can actually keep understanding, and that's really based on how well you write your code, whether someone can understand your complicated four-dimensional linked list with pointers going back and forth through the list and other stuff like that. That's a joke at the moment, but it won't be a joke later. Real things like that do exist, and a lot of us have worked with very, very strange extensions of this concept. There's a great deal of computer science that stems from this basic concept of I have this thing with some information, and then I have a pointer that leads to another thing that's identical in type but has some other information. So we go from this list of things that are joined up to like these weird spanning graphs of things and then neural networks and all this kind of stuff, right? We'll talk about that later. Well, we probably won't, because COMP1511's not going to go that deep. We need to get the basics, and we need to understand them first. It's hard enough as it is in a single line, let alone when it gets big. But, you know, there's plenty of time to learn that later. People are talking about what the hardware specs of their brain are. The brain's really weird. It's a very weird process. Let's not talk about that now. There are some very strange things that the brain does. So one of the last things that we did last week was we were looking at looping through the linked list and printing it out. I'll jump into the code in a second. The trick with the loop through a linked list is, I think, mostly the structure is not thinking about the end of the list being the number of elements in the list, because a linked list, even more than an array, is not necessarily going to have the same number of elements, and it's going to change in its number of elements a lot. So instead of it being looped through a specific number of times, it's very much more of the loop through until there's nothing left. And this is actually really similar to the loops we were doing on strings, where the strings just loop because they don't know how long they are, but when they hit the null terminator, they stop. In the same way that a loop through a linked list keeps going until the pointer that it's moving through the list is null. And if the pointer is null, it means that we've gone off the end of the list and we're no longer aiming our node pointer at a node anymore. We're aiming at the empty space off the end of the list. And so when we get that, we say, okay, there's no more to do in this list. And the other thing that we do is the way that we move through the list is we follow these next pointers. So I say I do something with this node, and then I follow the next pointer and I get to this node. Follow the next pointer, get to this node, follow the next pointer here, follow the next pointer here to null, and that's where we stopped. So what we're going to do is we're going to maintain one pointer that changes its address to each node in turn. So the first time through the loop, it's pointed at the first node, and then it says, okay, I'm going to copy this address, because if I copy this address, it leads me to this node, and I store that address in my pointer, and I move on to the next, which is this line of code here. I think, personally, the most confusing thing about linked lists is going from this image and thinking about moving pointers around in this image to like a single line of code, like this, where you go, how does this move the pointer? Right, and this goes back to what I was saying earlier, that moving pointers is about changing their value. So if I have an address, so I've got a piece of paper that I've written down an address, so 150 Anzac Parade. 150 Anzac Parade says to me, alright, the next house you need to go to is at 200 Anzac Parade. I'm just making these numbers up, by the way. I apologize if anyone actually lives there. I'm just using your houses as examples. So it says, alright, the next one is go to 200 Anzac Parade. So what this line of code does, it says, I read the 200 Anzac Parade from the place I was looking at, and then I say to my address, okay, I'm going to rub that out, and now I'm going to write 200 Anzac Parade there. And then the pointer that I'm holding, the piece of paper, then becomes a different address, and it's now aimed at a different location. So there's a bit of going back and forth between knowing how these, knowing how visually a linked list should work, and then getting pointers to move around. So we're going to get a bit of practice with this. You've already, if you've had your tutorial this week, so anyone who was yesterday has had a little bit of practice on this. Later tutorials we'll get to see a little bit more of this in the lecture before they go in. So there's a bit more about inserting here that you may use. For the moment, we've only inserted something at the very start of the list, so we've shown a really simple way of doing that, but today we're going to start inserting at other points. Oh, Lorenzo's asking, does head next work as a pointer to the third element of the list? Yes, it does. If it exists, you can do stuff like that, and there actually isn't a limitation to how many next you can have, because if you think about going into this struct and you go to the next, it takes you to another one of these, which means there's a next inside that, which takes you to another one of these, and there's a next inside that. So long as it's built correctly and there's actually data there for you to go to, you can do that. Once you hit the null, things get weird though, right? Because you've got to actually check. That's why saying like head next might be super dangerous, because you don't know at that point in time whether your list actually has stuff in it, which is usually why we loop through one at a time, checking for nulls along the way. Okay, so where we're up to, let me log in. Just in case anyone needs it, we now have this web address here. I don't know if you can see that looking at my screen over there. Unlikely that you can see that, but the link is, as usual, in the lecture section on the web page. All at the moment we have in here is the battleroyale.c, which is where we were up to last time. Which is this. So, sorry, this one's not a joke. But so we had our node, which was a player node that just contained the name of the player. So we're keeping it reasonably simple at the moment. We're still only keeping one variable in these. But if I wanted to, you know, it's pretty easy to edit this and say, okay, I want to keep score or something. Or I could have, I don't know, I'm just like making up stuff, right? Because like not many games necessarily keep score of a lot of things, but they might keep inventory or something like that. So, you know, famous battle royale games, if I'm going to do something like Fortnite, I would potentially want to know what items a player's carrying, so when they get knocked out of the game, they drop their items. Wait, do they drop items in Fortnite? I don't even know. I don't really play it. Okay. So, but I know like PUBG, PlayerUnknown Battlegrounds, you can steal stuff off people after you take them out. So anyway, we could have some more information here if we wanted to. So, but that's okay. For the moment, we're thinking about the structure of the linked lists and stuff like that. Okay. We had some functions as well. We have a type def here, so we're thinking if we want to think of this thing not as a pointer, if we want to think of it just as a concept so that we don't accidentally dip into here and cause issues, we can do capital P player. So if I want to start splitting this up into into different files, I could create a main.c, and what I'm going to do is I'm going to take my main here. I did Control X there to cut that and put it in here. I know that it is going to need to include an H file, so I'm going to call it battleroyale.h, assuming that I'm going to create that. So let's just create that now. And in the H file is going to have some of these important things like the hash define, our type def is going to go in there as well, and our function definitions are going to go in there also. We probably don't need something saying functions in here. Create a player by allocating memory. Put a comma there. Populating their data. Then returning a pointer to them. A good example of what an H file looks like is the H file in the second assignment that we have now, where it has a whole lot of comments in there and a whole lot of detail on what each of these things are, but it doesn't actually include, obviously, any of the implementation, which we leave in the C file for you to do. So a C file would look a little bit like this. It's got whatever struct is going to be used, as well as the actual functions working. I might actually take this comment, copy this, and put it in the main. The main is usually where you'd want this, but what I'm going to do is I'm going to put it in each of them and say this one's the header file. This is the main file, and this is the implementation file. Okay, so what I've just done there is I've separated our initial single file project into a multi-file project. Ooh, someone just asked, when did the last 2 lectures get uploaded? My apologies. The last 2 lectures will get uploaded when I upload them, which means I obviously haven't done that. So I assume that you're talking about the Echo 360 thing, because I haven't copied and uploaded those. So I will get to that soon. Unless you mean YouTube, in which case I've made a mistake and I haven't flicked them over to public and they're still unlisted. But I'll check on both of those things afterwards. So Deluxa, I assume that's how you how you pronounce your name. I'll check on that after today's lecture. Okay, so we're in a situation now where we have, I'm going to put the main there, and the H first, then the C. Sometimes I like them in this particular order. So, the C file has these bits and pieces. The C file is going to need to also include the H file, or else it won't know which functions it's creating. The H file tells us which functions there are. Right, so I've got some comments in here in the header file as well. The hash define, I guess I'll leave it here in the H file. Sometimes some hash defines will go in the C file, some in the H file, but might as well leave it there. Okay, just to make sure that I haven't moved anything to the wrong place, I'm just going to check and compile this whole thing. So, remembering, when we compile a multi-file project, we compile the C files, and we trust the C files to include the H file, so we don't need to compile the H file. I'm just going to change my directory so that it's a bit shorter and I can see things more easily. So I'm going to DCC the two C files that I've got here. So if I have a look at this, you can see battleroyale.c, main.c, and battleroyale.h. Don't worry about the backup files, we're not going to use them for the moment, unless I accidentally delete something. So I've got my main.c and my battleroyale.c, and the output, I'll just call it battle. Oops. Use of undeclared identifier null. Alright, so I've got a problem here where I think it's my main.c, line 14. I've got a null in here, and because I didn't have any includes to use it, then I don't actually have the capability to use a null. I don't think I'm necessarily going to be using nulls once I get deeper into this, but I know that I'm going to need something for the moment. Nearly all of the standard libraries have null in them, but I know that standard lib has it definitely, so we'll try that. Okay, so we're compiling. Let's run it to make sure that it's got its basic behavior. So, Goku, Aang, Chicken, Mark. So remember, each of these insertions we were doing here was replacing the start of the list and moving the list along. So when it prints out, it's going to print out in reverse order. Okay, so that's where we're up to. We've got two functions, one to create a player and one to print them out. And what we're using is a simple way of just calling the create player function multiple times to add something to the start of the list. So that's where we're at so far. I think this is everything that this is the stuff I've already just talked about. Yes. Oh, in case you need it, you can go back and look at these things in the slides, but it's in the code as well. Yeah, so I've just talked through all of this. I don't need to look at those slides. So let's think about what's next. What's happening now? That's all right. I think Michael's answering all the questions there. Okay. So, I wonder if I need to talk about the type define. I think we've talked about this a little bit, but it's probably worth looking at it. So the type define here, we've got a struct player pointer that we're now calling capital P player. So we use player instead of struct player pointer, so that when we're using it here in my main, that can't see what's in the C file, it can only see what's in the H file, we can start to think about this as a concept of a player rather than a concept of a pointer to a struct. Because there's no point having a pointer to a struct if we can't access the internals of the struct. So we don't want the main file to be able to access the bits inside the struct, because if you could, that might mean that you'd be able to change where the next pointer is in a struct, and then suddenly our linked list would get broken, right? We don't want the linked list to get broken, so we want to control what we can do here. And so for the moment, the only thing we do is create a player, and once we've given it a pointer, there's nothing else that we can do to edit it. So we're kind of protecting our data in a sense. I'm going to talk more about this later, actually. Next week, we're going to do more building up of these multi-file projects and the concept of abstraction, which I'll talk about more later. Okay, so this is where we're up to, and we think about what's next. So the next thing we're going to do is add players to the game. So we've already had the ability to just kind of build up a list, but that was only at that point allowing us to insert things at the very start of the list. So we're thinking about not just inserting at the start of the list, but inserting anywhere in a list. So we want to be able to loop to a certain position and then insert there. And then we're going to think about, even better than that, is if we're careful about our list and we keep inserting in specific places in our list, what we can do is we can build a list that's in order. The idea of creating batches of data and then keeping them in specific orders is something that's like, it's pretty big in computer science, because if we can organize our information, it's easier for us to find things. There's heaps of stuff that we do in computing which is basically just trying to make that stuff go faster. So can we find something more quickly? And if we can find things more quickly, then a whole lot of our other parts of our programs run faster. we're not worried too much about that in 1511. 1511, we're trying to teach you just how to get things going. Not how to make them go really fast or anything weird like that. But you will definitely be doing that later if you're going to continue on with computing. So for the moment, what we're going to do is we're going to try to keep a list in alphabetical order. So what we're going to do is make sure that every time we insert into the list, it's going in alphabetical order. And if we can just move through the list and insert in specific places, we can end up with an ordered list. So first thing that we're going to need for that is the ability to insert anywhere in the list. And then the second thing we're going to need in the list is to be able to check where we are in the list and then insert into it. So few different things like that today. So the first thing we're going to do is we're going to insert into the linked list. Doing this involves moving pointers around. And I just kind of do this, like, it's funny as an illustration of the difference between what it's like to think about this in text versus what it's like to actually think about it in an image. And this is my way of trying to convince everyone to draw lots of pictures when you're working with linked lists, and it makes it easier. So if we move things next pointers around, we'll be able to insert something into the list. So if we have two nodes, we want to put a node in between them. We can take the next pointer of the first node and aim it at our new node, and then we take the next pointer of the new node and aim it at the second node. And this is like, yeah, okay, if you kind of know what's going on and you're really clued in, you can understand what I mean when I'm saying it here. But it's much easier if we draw pictures instead. So here's a picture of a linked list before we've inserted anything. So this is really simple when it has a first node and a second node. The numbers are reversed, but don't worry about that. So there's a head into the first node next into the second node next into null. Well-formed linked list because they're all joined together. And the last one specifically says, okay, we finish here. So I want to create a new node. I can create a new node. So this one is calling this one kind of number 3, but we're calling this one first node, then second node, then new node. So now that I've created my new node, what I want to do is I want my linked list to still be connected. So I need to connect this new node to the list. And there's a few ways that I can do that because I do know the addresses of the first node and the second node. And I know that the new node is going to have to slot in between these two. So the first thing that I can do to make this work is I can say, okay, new node's next pointer should be pointed at the second node. And so I say, how do I find out where the second node is so that I can point new node's next pointer at it? And I go, okay, that's easy because this thing used to be connected up. Well, it still is for the moment. It's still all connected up. So I know that first node points at second node. So what I'm going to do is I'm going to take whatever is stored in this pointer and put it in this pointer. So if I take whatever's stored in this pointer and put it in this pointer, I end up with this. This pointer now aims at the same place. So whatever value is in first node's next, I copied it into new node's next. So new node is now connected to second node, which is one step closer to this thing being a complete linked list. However, we can never get to new node because nothing in the linked list is pointing at the new node. So now that I've connected this up to this, I know that it will continue to the end of the list. So the tail of the list, we call them head and tail a lot of the time here, is correct. But the first node is not actually connecting up to the new node. So what I can say is the next to the first node should probably point at this new node. So hopefully when I created this thing, I kept its memory address, because if you don't keep its memory address, then you don't know where it is. So now I need to connect this up. So I'm going to say the next to the first node is going to point at the address of the new node, and I end up with this. So my new node's next was set up to be the second node. I had to copy the first node's next to do that, which means that I can't do this step first because I still need this information here so that I can make a copy of it. But after I made a copy of it, then I can say the first node's next points at this new node. And so if it's now pointing at this new node, you can see that we've got the head pointer points at the first node. First node's next pointer points at this new node, which has just been inserted into the list. This new node's next pointer points at the second node. Second node's next pointer points at null. There we go. We now have inserted an element into a list, and it's finished up as a completely well-formed list. Ooh, break time. No, I don't think we'll take a break yet. I've got some fun stuff in that break. I've got some homework for you. It's homework. It's like fun homework. So I think what we're going to do is continue, and then when we hit a good time for the break, I'll come back to that slide. So we've got some code here for inserting players. I'm not going to talk too much about this slide. This is like way too much code at once to just talk about. So I'm going to build this code up bit by bit and show you how it works. So what we're going to do is we're going to add a function to our program. So the first thing, if we're going to add a function, is we're going to put in the H file so that both of the other files know what this function is going to be. If I remember correctly, I was going to, yes, insert a player into a list after a given player pointer. Actually, let's call them capital P's here, although this isn't necessarily a capital P player. This one's a pointer. There you go, player node. So I'm going to keep it really specific what's going on. I think I'm going to return... I remember what I'm going to return is the... Actually, it's not super specific what I'm returning here, so let's write this and then I'll think about what I'm returning afterwards. Oh, I'll show you something you can do. I'll put this in brackets like this. When you use this capital TODO, to do, it actually highlights it in your code. So what you can do is actually leave these in your code for yourself to say, oh, I need to come back and figure out exactly what this thing is, and then come back and do it. So a lot of the time when I'm actually working in an H file, what I'll do is I'll plonk down a whole bunch of functions that I think I'm going to need, and then I'll put a to-do in a comment next to each one of them that I haven't completed yet. Or I'll come in here and I'll do something like this. Let me write the function itself. So it's going to return a player, and it's going to be called insert after. It's going to need an insert position, and then it's going to need a name of the new player. I'm going to call it new name again because we were using new name every time we were creating a player. This thing's going to need to create a player as well. So this is what I think my function is going to look like. I mean, I'm open to changing this once I start implementing it, but I know that I'm inserting a list after a given, inserting into a list after a given player. So I'm assuming that I've been given a pointer to somewhere in a list that already exists, which is a pointer to a player, and then I'm going to create a new player with a given name and stick them after that player in the list. So I think that this is all the information I need for this function. So I know what it's called, and I think I'm going to give back the information about where I inserted. Okay, so I've got this, and I go into my C file, and I go, okay. And it's going to be a similar comment, I think, but I'm going to put a comment in here anyway. Sometimes when I get into the C file, there's more detail in there. But what I can do now is something like this. Sometimes I'll just leave it like that, and I'll be like, okay, I've got to go back and do that. and I'll come here and I'll do other work and stuff, but I'll just say, remember that I'm going to need to have an insert after function at some point. But then since we're already here and we're working on this, let's get right into it. So, reasonably complicated function. I have talked briefly about the theory of moving these pointers around. But what I would want to do in a situation like this is make sure that I've got a good framework to start with. So again, this is the kinds of things I'm trying to help everyone out with, is the step-by-step process of building this thing, rather than just typing out the code, so I'm going to go through my whole process, including the to-dos and stuff that I might do while I'm doing it. So the first thing that I would do is create the new player. So I'm going to follow these steps here. So I'm going to assume that I've got a linked list, and I'm going to assume that I was given a pointer to the first node, and I'm inserting. So let me draw this so that it's reasonably clear what's going on. I'll just put in, oh wait, nah, I'll spell it out. I was going to put an X for null. So I've got these two things here. And then, let's say, head. Apologize for my mouse writing. So the head point's here. I don't know if I'm going to need the head for insert after, but maybe later. At least what I'm saying is this is a well-formed linked list. And let's just make this node 1 and node 2. I know they're going to be names, but I'm just numbering them for the moment. So the first thing I'm going to do is I'm going to create a new node. Actually, even before that, this function has been given an insert position. So if it's been given an insert position, then I know that somewhere I've got a pointer to something in this list. I'm going to make it a pointer to number 1 to make it easy on ourselves the first time we implement this. When we start working with these things, you'll notice things get weird if you're trying to insert A into an empty list, or you're trying to insert into a after the end of a list. Like, there's little fiddly things that we might need to deal with. But I'm going to start with the most simple example here, I guess. So we've got a pointer to the insert there, and we're saying we're going to insert after this. So first step is we're going to create the new player. Then we're going to follow the steps in the slides here. I'm going to say, first thing, we create a new player. Second thing, we copy the first nodes next. Third thing, we move the first nodes next to the new node. And that's it. So we're at this step now. We're going to create a new player. Then we're going to copy the insert positions next into the new player. Then change the insert positions next to now aim at the new player. So if I've got these comments in here, it kind of breaks down the problem for me into a step-by-step thing. I can ignore these two steps while I'm working on the first step. So, create a new player. What would I need to do to create a new player? This makes it easy on us because we have a create player function already. So, let's say that I kind of want to call it new, but I think that I should call it... Oh, I'm going to call it... maybe I should just be like... sometimes I try to shrink my variable names so it's easier for me to type stuff, but sometimes it's like, nah, just make it easier to read instead. So I'm going to call it new player. I think I did it up here anyway. Yeah, I called it new player. And the new player, so this thing, create player, returns a player, so I know that I can store the player in new player if I call create player. And I need to look up here and say, okay, what information did the new player need? It needed a name and a next pointer. So the first thing is we give it a name, which is the new name. And then we give it a next pointer, which is kind of cool because we have another instruction here that we're supposed to do, which was to say that insert position's next pointer is the next pointer that this new player should have. So we can actually do both of these things in one step. So what I'm doing is I'm creating this thing and I'm setting up its next pointer to be a copy of this node's next pointer like this immediately. So, new one here. And when we create it, I'm just going to call it new. We'll get given a pointer to it. So let's just call this one number 3. But the interesting thing about it is as we create it, we can copy number 1's next pointer. Copying its next pointer means that this thing will aim at the same place that this one did. So we're just copying both of them have the same value in their next pointer. So what I can say is if I'm copying the insert positions next, I'm going to say insert position, and I know insert position is a capital P player, which means that, especially now that I'm in the C file, I know that capital P player is the same as a pointer to the struct. What's in the C file knows what the struct is, so we can access the fields inside the struct. So if we can access the fields inside these structs, I can say, because this is a pointer, I use the pointy accessor to get the thing inside, and I say take the next pointer from the insert position and make it the next pointer of the new player. So that's me saying, look at the insert positions. Actually, I'll just use this so you can see my pointer more clearly. Take my insert positions next pointer, which is the data in there that says next, that gives us access to node number 2, and we're going to make a copy of that here. And we've made a copy of that here, which means now this node 3 also has access to node 2. So both of them have pointers to node 2. And I can do that by just saying, when you make this thing, make its next pointer the same as the next pointer that we can see from this one. So this is actually I've shrunk down what I needed to do there. Then what I can do is, after that, change the insert positions next to now aim at the new player. So the state where it is here, and then what we want to do is this change. So this first node used to be connected to the second node, but what we're saying is we're putting the new node in between the two of them. So we need to link this up like this. In this image here, what I'm doing is I'm saying, we don't need you to connect to this node over here anymore, because this one now connects to that. So what we do then is we take this here, this pointer that aims at number 3, and we're going to copy that pointer into the head, which is going to give it access to this node here. So this new pointer is pointed at node 3. If we copy that new pointer there, number 1 will now be pointed at this node here. So change the insert pointers next. So we're changing its pointer to aim at the new player. So if I'm going to change a pointer, I'm going to take its next. Oh, sorry. I need to say which things. So insert positions next pointer is now going to be something else. So this is, using the equals to change the value of a variable. So I'm going to change the value of this variable to the address of new player. And it's really interesting because new player is a capital P player. Capital P player is a pointer to the struct player. So this is already, capital P player is already a memory address. So all I need to do is just copy new player, because new player is a capital P player. So this is a memory address of a player. So I copy that there, like that. This is actually all it is for the insertion, which is why I had to spend a whole lot of time talking about this and drawing pictures and stuff, because if I'd just written these 2 lines of code and said, oh, this is it, fine, you're done, I think this would have been very confusing. So linked lists are really weird like that, where you have to spend a lot of time thinking about it, a lot of time figuring out exactly what you want to do, and then write very, very small amounts of code. So it's kind of thing where, like, you don't want to count the number of lines of code to judge how hard something is, because I would say this is very, very hard, but not very many lines of code. So we had to think about where these pointers were going and how we were setting them up, and then how we were going to change things to make things work. So this works for some of the things that we're doing. So this works if we're inserting in between nodes. It actually also works if we're inserting after the 2, because if I was inserting, say, a new node called 4 after the 2, what I would do is 4 would copy 2's next. 2's next pointer points at null, so that's a pretty easy copy there, and I would take 2's next and then point it at the 4. So I would do this. So we can insert at the very end of the list like this if we know, obviously, 2 would be the insert position there. But we may have some issues if we're inserting into a list that doesn't exist. This also doesn't give us the capability to insert at the start of a list. So if I'm inserting after the head, I always have to be the second element. However, we also already had some code from before to insert at the start of the list, so we've got that if we need. But we do need to deal with the possibility that this list is empty before we start inserting. So if my insert position is null, that means that there is no list. So the head of the list is pointing at null. We'd still want to be able to insert into an empty list. So what we need to do is, before we start grabbing all these bits and pieces, because maybe I'm going to save that one as insertion, just in case. If I had the following, so if I had this is weird, right? Because we haven't looked at this before. This is a linked list. This is a perfectly valid linked list. The head is pointing into the list, and then the final element of the list is pointing at null. So what we're saying here is that it's empty, but it's a working linked list. Like, we could loop through this. I mean, the loop would never run, but we could loop through this. And we need to be able to work with these circumstances. So what if my insert position is this head, which happens to be null? I need to actually check for this. So if... Oh, sorry, we didn't actually do the final point, which was we're just going to give back the position that we inserted into. I wonder if we want to give back the position we've inserted, or we want to give back a pointer to the new node that was created. I'm not sure. This depends on how we're going to be using this. I am going to leave that as a to-do, because insert after is rarely going to be used on its own. We're going to be starting to use it with other things. Okay, so the thing that I wanted to check for was, if the insert position is null, we're inserting into an empty list. So I'm going to assume that we're inserting into an empty list, because if someone wanted to insert at the start of a list, they wouldn't give us a null pointer, because giving us a null pointer just gives us access to no list at all. So that wouldn't allow us to insert into a list that already exists. The null pointer gives us no information, so we're assuming that if insert after gets called with a null pointer, the program wants us to basically create a new list like that. So if we're inserting into an empty list, we're probably still going to do the same thing. We're going to create a player, but we know that we can't do insert position next, because if insert position is not a node, it has no next. So if it's not a player, it has no next. So if I was just to run this function, let's just copy paste this function here, I'm going to cause some serious issues, because this, you can't do the next of a null. So for example, this doesn't have a next, so there is nothing here. The null doesn't have a next field. So let's reopen my last one. Where did I save it? Insertion. I won't bother saving that one for the moment. Each of these has a next because they're actually nodes that exist, but the null doesn't have a next. So we can't just go next like that. What we can do is say that if it's an empty list and I'm adding a node to an empty list, I know that node is the last node in the list. So it will be null. So my head was pointed at null. If I create a new node, I know that it's the only node in the list because the list was empty. It can be the last node pointing at null. When I point at null and I actually draw null on the screen, I just want everyone to remember that it doesn't exist. Null's not a place or a thing. I just happen to be pointing at a thing on the screen because I have to write null. Otherwise it's hard to understand what that actually means. These pointers are not actually aimed at the same thing. They're both aimed at nothing. So if I'm going to point that at null, and this is now the list, so I'm just giving them numbers. Actually, they don't really, this one doesn't need a number. I'm going to leave the number out. So I've got this and it's pointed at null. So this is my whole list now. So I have a pointer to this, which is going to be my new player pointer. And then what I need to do, because I've basically just created a list, I might need to give the rest of the program access to this. So when I was inserting here into a list that already existed, I didn't have to give back a pointer to this thing that I'd created, because it was linked up in the list. The insert positions next was now pointing at it. It's all connected. We don't need to save its address because we've actually saved its address in one of the other nodes. But this one, there are no other nodes with which to save the address. So what we need to do is actually give back this new player's address. So I know that when this finishes, I'm going to give back the insert position. So what I'm going to say is save the new player's address in the insert position, so that when I give it back, it's going to say, you were inserting into an empty list. I'm going to give you back a pointer to this new list that we've created, just so that you've got it. I also want to make sure that this is the code if I'm creating a new list from an empty list. This is the code if I'm adding to a list that already exists. If I'm adding to a list that already exists, I'm only doing one or the other of these two things. So I don't want to do both of these things. So I'll put them in an if-else, like so. Tab that in like that. And I've got my return here at the bottom that says, there's a couple of things I was doing. I was either inserting into an empty list or inserting into a list that already exists, which I might say here. Okay, so this is my code that is going to, I don't know if this is even the same as in the slides. It looked like there was more stuff in the slides. I'll find out later if I've missed something important, but you know, that's coding. We don't expect everything that we create is going to be correct first go. So I know that if I insert into a list that already exists, I'm just going to get back the same pointer that I gave in. So it's just going to say to us, you gave us this position to insert into, we're going to give you back the pointer saying, okay, this is done correctly. If we try to insert to a list that doesn't have anything yet, we're going to get given back the address of the thing we just created. So we're going to create the list like this, which is good. Okay, so we've got our function here. It's 12:04 though, so let's take a break, and we'll come back and test this afterwards, as well as doing some other work with it. Where's my break? Wow, my break was way back there somewhere, wasn't it? Nope, nope. Ah, here it is. Okay, random homework. It's not really homework. This is more just like kind of interesting things that you might get into if you're interested in computer science. So, a couple of things like, there's a lot of fiction in here as well, which is just fun. AlphaGo is real though. It's a documentary on YouTube. There's a channel called DeepMind, which is the now owned by Google AI Institute, I would call it, that they're working on a lot of things with deep learning neural networks, and some of the stuff they're doing is trying to get into spaces where human intelligence has been kind of pushed to its peak, and seeing if they can compete at that level. And the game of Go is one of those. Really interesting documentary. Some short stories about robots and artificial intelligence. There's other stories about the idea of like hacking the human brain or cryptography and stuff. Neil Stephenson does a whole bunch of things which are sort of looking at history through a different lens. So it's like sci-fi, but instead of being in the future, he actually looks at history and changes things, which is quite interesting. The Cryptonomicon's one of those. And sneaks in a lot of stuff that's real computing as well, so I think that's quite interesting. Human Resource Machine is a really funny game on Steam. I think I've mentioned this one before, where if you play Human Resource Machine and then you spend some time with it and think about it, and then you do, I think it's 1521 or 1531, I can't remember which, no, it's 1521, the course, you'll find that this is the same language. It may be a game and it's fun and stuff, but it's actually teaching you assembler while it's there. So it's the stuff you do in the game is an analog that's exactly the same as the assembly programming language. And then I threw in a board game here, which is a board game about programming your little player on the board. So instead of like rolling dice and moving in a board game, you say, I will do this, then I will do this, and I'll do this. And then at the end of the phase where you're picking what you want to do, everyone kind of flips over all of their stuff, and then their player has to act out the path, the sequence that they've programmed for the player to do. So interesting little things where you can do some kind of simple programming and stuff while you entertain yourself or get inspired about technology and making technology and things. So fun little things like that. Okay, so let's go on a break. I think it was 12:04 before I started talking about break time. So let's go on a break. It's 12:08 now. We'll make it a 4-minute break, so there's time to come back and do more code. So at 12 past 12, we will come back and do more coding. Alrighty, I'm back. Talking a little bit about playing computer games that help with programming, or even just not even help with programming, just like are fun because of programming, or they're interesting because they take some of the concepts from programming and make them into entertaining things. So we were talking before about Human Resource Machine and the sequel called 7 Billion Humans, but there's like an entire genre of these games. Because strangely enough, a significant number of the people who make computer games are programmers, and so there's always going to be a significant number of those people who love programming as much as they love playing games, and they thought, oh, why don't we just throw these things in together and make programming games? So you can check them out. I know Steam has an entire category of programming. I can't remember if it's called programming games or just programming on Steam, and then like you see all these kinds of things, and there's some really interesting stuff in there. You can check it out if you want. So my homework list is not the only homework list. I also notice here that it's like books and games. There are heaps of movies that have programming in them as well, in different ways. Plenty of them have programming in them, which is like just like hacking the system and stuff, and not quite as interesting. But some of them are more genuine. Some of them have actual kind of questions about the nature of, controlling machines and stuff like that, which might be interesting. I think War Games was a good one. Old movie, 1980s. There's a lot of them that are more recent that are a bit like, I don't know. Like, I think Hackers was a little bit, and Swordfish was a bit like, So, Hollywood's always going to be doing some stuff which is a little bit weird. Okay, so where are we up to in our code? So we have created the insert after function, but we have not yet tested it to see whether it works. We're talking about people are just talking about little things like that. Someone was saying DEF CON. Yeah, actually, even games like Factorio and Satisfactory like scratch the kind of itch. I played Satisfactory over New Year's when I was on a break, and I think I got to the point where I was like 16 hours a day in that game, and I was like, alright, okay, I'm done now. I've deleted it since, and I've just been like, don't go back to that game, especially not if you want to like keep your job. Okay, so we've got our insert after, and we know that insert after is here. Oh, return, specify exactly what the return is. Good, I can do that now because I've written it. Returns the insert position or a pointer to the new list if it had been given an empty list. Right, so now I can specify that. I like the to-dos, they remind me of things. Oh yeah, people are talking about Minecraft Redstone. Someone was saying that I should do an entire lecture or an entire course in Minecraft Redstone. I thought that would be really funny if we did something like that, and it was like the attendance to the course wasn't like a live stream or something like that. It was like you literally hop on the same server, and then we'd be like, all right, everyone get your own little piece of this thing and build the same thing I'm building. I think that could be quite interesting. I don't know what the server limits are on those things, but Okay, so if I've got the insert after function, I'm just going to copy this here. Then I may not need this anymore to create a list. So what I could do is, instead of create player, I can say insert after, and the inputs for insert after are the insert position and then a name. So let's start like this and say, okay, the head is null, so we're going to create an empty list, and then we're going to insert after, and I think this was the other way around. We're taking the position first, which is the head, and then we're getting the name of the new person that's being inserted after the head. So here I have insert after, taking the head, and then putting me after that. This is not going to change this list, because this is pointed at null, so there's nothing there to change. So what I'm going to do is I'm going to say, give me back the pointer of the thing that you've just created, which is me. I'm going to get rid of all of these and just test this and see how this is going. So hopefully what we're going to get is I've created an empty list. I've inserted something into my empty list and then got given back the new list, which is now going to be the head, and I print this out. So hopefully this works and it prints out my name. Gonna compile this, run it. Good start. Lucky. Sometimes I feel like I need to write more code that doesn't compile first go, because it's a bit unrealistic to expect all this stuff, especially I just split up into 3 files and then added functions and stuff like that. More often than not, when you're working like this, you're going to see things that doesn't work rather than it does. Having said that, I guess we don't have much time in lectures for me to do a full debugging thing. Okay, so I now know that insert after could create a list, and I can keep inserting people. But this time I could do interesting things, because if I insert after the head, I'm the head of the list. So this is going to make whoever I put in next the second person in the list. So I'll put chicken in as the second person in the list. But then I could do another insertion, and I could say if I'm inserting after the head, so this is the situation we're getting here. So first of all, I had my head. Alright, there you go. If I'm careful about it and don't try to do running writing, you'll still be able to read what it is. Head was null. And then I created a player for myself. And it pointed at null. And then what I did was I said that the head was equal to the one that I just created. So I go, okay. Head now points here. And then I did an insert after using the head as the insert position. So the head is now me, and if I insert after me here, chicken, insert after head, head is still me from the previous line. Then chicken is inserted after me. Where's my paint? Here. So we create a new one here. Called chicken. And I am now no longer pointing at null, because I will be pointing at the new node, because we know that our insert after is going to do that for us. And then chicken will be pointing at the null. We did, in this code, say that the head is equal to the result of the return of this function. And so if we want to be careful about what the return of the function is, it returns the insert position. So it just gives back the same insert position. So if I gave it the head, it gives back the head, and it's going to be the same thing. The only time that's going to change is or a pointer to the new list if it had been given an empty list. And so at that point, it wasn't given an empty list. And so we can insert another person. We were doing avatar stuff last time, so we can insert Ang after that. But Ang's also getting inserted after the head. We don't really need to even worry about these, because we're assuming at this point that the head's not going to change. But if Ang's inserted after the head, that means the head is still me, so we've got this insertion here between me and chicken. So first thing that will happen, Ang will copy my next pointer to point at chicken, and then my next pointer will then point at the new node here that has been created, which is Ang. So we're starting now to be able to insert things in different orders. So this then, if I've done this in this order, should print out my name, then Ang's name, then Chicken's name. Even though you see we're doing these things in a particular order here, because we're doing insert after the head each time, each new insertion becomes the second element in the list. So I became the only element in the list, then Chicken becomes the second. Ang becomes the second element in the list, pushing Chicken 1 along. So let's test this. I'm going to compile and run it and make sure that's actually doing that. Mark, then Ang, then Chicken. So this follows what I said should happen here. Myself, then Ang, then Chicken. Because we're now using the capability to insert in between other nodes in the list. Okay. That's probably okay for now. I say probably because I'm never going to say something is working unless I've tested it a fair bit. But I'm pretty sure this is working for now. So we've got the ability to insert in between players. I think when I did this here, I did it with different code, but you know, similar kind of thing. Now, what I said was we were going to try to insert into a list in a way that was going to keep this list ordered in some way. So what I'm going to do now is I'm going to start comparing the names of players and deciding where to insert them in the list. Because when you think about it, one way that we could organize this list is alphabetically, and at the moment it's definitely not alphabetically ordered. Ang should go first, then Chicken and myself, so this is like very, very not alphabetically ordered. But if we do this in a particular way, we could alphabetically order this list, so that's what we're going to try to do. So we can look at the strings in each node in the list. We can loop through the list. We've got both of these things we've already learnt about. So if I loop through the list, looking at the strings in that are in the nodes, compare them against the string that I've just created and I want to insert somewhere in the list, I should be able to find somewhere in the list that my node should be placed. And so I'm going to use a string library function for this called strcomp, short for string compare. String compare is pretty weird because it compares two strings and returns 0 if they're equal. It's exactly the opposite of what I would like for a sort of true-false question. Because it's not a true-false question, it says 0 if there's no differences between them, and it's negative if the first of the two things put into string compare had a lower ASCII value than the second, or it's positive if it had a higher ASCII value than the second. So when I say lower or higher ASCII value, it's going to look at the first letters of both words, and if they're the same, it's going to go on to the second letters of both words. If they're the same, it'll keep going, basically until it finds a difference, and it'll show you the negative or positive. Or if it gets to the end of the strings and they're the same, we'll get the 0 out of it. Michael's answering a lot of questions there. I'm going to leave them with you, Michael. Someone's asking about sorting methods. We're not actually sorting a list here. So we're not taking a list that is out of order and putting it into order. And there's a whole field of computing, which is all about taking lists that aren't in order and rearranging them to be in order. What we're doing here is we're just putting things into the list and making sure they're in order, and then that list will always be in order if every time we insert into the list, we insert in alphabetical order. So we're going to use string compare for this, and finding where to insert involves looping through the list that we already assume is in alphabetical order, and we're going to assume it because everything that we put into it, we're going to put in alphabetical order, so hopefully that's going to keep the same order. So long as we don't move anything around, we'll be fine here. So we're going to loop through, and we're going to test using string compare, and then we're going to stop at a certain point in the loop and say this is where we're inserting. So I'll show you in pictures here, which is a nice way to think about it. So if I have A, B, D, E, so I've got the letters here, and obviously the letter C is missing. What I want to do is I want to compare C against each of the nodes in the list, and then see where it should be inserted. So my loop starts at the first element of the list. The loop always starts as a copy of the head. And it compares A and C, and it says A is before C. So if A is before C, then my loop should move on. And it goes here and says B is before C. So if B is before C, I'm going to move on. And then it gets to here and it says D. Oh, D's after C. So if B was before C, and D is after C, then I know that I need to insert in between those two. So the pointer of my loop is going to stop aimed at D, and the only little issue here is because the pointer of my loop is aimed at D, I have a function that says insert after. I don't have a function that says insert before, because insert before is really hard to write, because we don't have access to any of the nodes before us in the list. We only have access to the nodes after us, because the next pointers are all going in a particular direction. So what I will do is I'll have this pointer that tells me where the loop stops, but I'll keep track of the node that was just before where I was, and I'll say insert after this node. So the first thing I do is I loop through, and I say I should be after this letter, I should be after this letter. We're going to do this with words. Same thing though. I'm good. This word is after this word's after this word, and when we go this word's before this word, I have to stop here and say insert before this thing, which means we insert after the last node, and it goes in between these two. Here's a whole lot of complicated code. Let's write it instead. I just have it all in the slides just in case people want to like really go through and look at that in detail. But we're going to now use some of the stuff we've already created, like this insert after, and we're going to insert alphabetically. Interesting thing that's going on here is I'm going to, partway through the creation of this thing, probably come to the realization that insert after is not something that I want in my main. Because I may actually not want my main function to ever just grab a list and insert into a particular position into it. Insert after might be one of these functions that exists in the C file only and doesn't get given to the other parts of the program in the H file. I'll keep working as if it is something that we're going to keep though, and then we'll see what we think about it afterwards. So inserting into a list alphabetically, I'm going to say, I think from memory, that what we're going to give back from this function is the head of the list. So we get given the head of the list, and we're going to give the head of the list back. However, because we're doing an alphabetical insertion, the head of the list might now be a new element. So for example, if I'm inserting alphabetically and I say Mark, and then I insert chicken into that list, the head of the list is actually going to change, because the head used to be pointed at me, but chicken will come before me in the list, so there'll be a new head of the list. So that's what my intuition says that that's what we're going to return, is instead of returning just where we inserted from or something like that, we're going to give back the new head of the list if it's changed, or the old head of the list if it hadn't changed. So we're definitely returning a player. I'm going to call this insert alpha, and what we're going to do is get given the head of the list and also the name of the new player that's going to be inserted into the list. And so what we're going to do is, it's like, it's quite similar to this insert position. It's definitely going to be using the insert after function. The insert after function is also using the create player function. So you start to see now why we build things into functions, because each of these functions has just one job, and you build up your complexity by going, okay, we're going to use this thing as a one line in this function so that this function's not too complicated. We use this as a one line in this function. If I had insert alpha and I didn't have insert after or create player, my insert alpha function would be like multiple pages of code. The more code you stack together in one place, the harder it is to find any problems in it. So this separates each of these things out into their own, not a huge amount of code. Also not a huge amount of code. If something goes wrong in one of these functions, there's not that much for me to look at. But if I tried to put this all into one function, which is the insert alpha function, I potentially could get in a lot of trouble there. So let's go insert alpha. Let me just do that so you can see it more clearly. So it assumes the list is already in alphabetical order, returns the head of the list. It may have changed. Okay. Again, this is a big function. Break it down into parts so that we understand what we're doing with it. Loop through and find the insertion point. Fighting my autocomplete here. So we're going to loop through the list, and we're going to remember that the insertion point is go past any names that are earlier than us alphabetically. Stop when we reach a name that is after us alphabetically. I know that these comments are way more than I need to describe my code, but for the moment they're what I need so that I can write my code correctly. So, in order to loop through and find the insertion point, I've been given a pointer to the head of the list. I can make a new one if I want to. People often use the short CURR just to be current, to short for current. So, current is equal to the head of the list. We're going to loop through. We're going to do a standard while loop on this for the moment because we know we're actually going to have a particular stopping case. So, but we will still be stopping if it's null. So if it's null, that means we made it to the end of the list. And current equals current next. So I've set up my while loop here by saying start at the head, loop until the end, one node at a time. I can probably put these together because this is all just the structure of a basic while loop. So I'm saying go past any names that are earlier than us alphabetically, stop when we reach a name that is after us alphabetically. So I want this while loop to stop under certain conditions. So I'm going to say if you get to the end of the list, stop. Or, oh sorry, it's not an or because this is the stopping case. Oh no, it is. Stop if you reach the end. Or, earlier than that, stop if the name that we reach is after us alphabetically. So I'm just going to come up here and make sure I've got my string.h. I do have my string.h. And I know that I'm going to compare things alphabetically using COMP. Now, probably, even though I've defined it on the slides, I probably want to go through and just have a quick look. COMP in C. There's lots of different places where people have put information about C. Oh, you can see I've been there. I visited this page 3 times. So you can see I go back and I look at these C standard library stuff, right? This is a point where I'm saying, yeah, memorizing these things might make things a tiny bit quicker, but a lot of what we're doing with these is going to be, that's awkward. I've got ads turning up in my lectures now. And they won't go away. Go away. There you go. It's nice to just know that there's references for these things, and the standard library is not something. I'm not asking you to memorize it. It's not something that, like, sure, it might help a little to memorize it, but what's more important is to remember how to use these things, not exactly all the details. So, string 1, first string to be compared. String 2, second string to be compared. If return value is less than 0, indicates string 1 is less than string 2. If it's greater than 0, indicates string 2 is less than string 1. Okay, so we've got that. That's a little bit hard to memorize, but let's put our 2 strings in and see what we're looking at. So, if current is not null, Interesting thing about OR statements like this, they go left to right. So if my current was null, this string compare would never be run, which means that if current is not null, and then we come in here, then we would check this. I'm thinking this actually is an AND, not an OR, is it? I wonder if people had already noticed that. Someone was asking if we can use the internet in exams. Yes, you can. Lorenzo noticed that. Should be AND, yeah. So if current was null, we would just stop here. The while loop would stop. So we're going to say that for this thing to be valid, we want, for this thing to keep looping, we want us not to be the end of the list, and we want to be skipping over things. So go past any names that are earlier than us alphabetically. So if we take the current's name, it is name, right? Yeah, it's just name. And we compare it against the new name that we have been given. Then we want to say, go past any names that are earlier than us alphabetically. So we want the first string to be lower in value than the second string. First string lower than second string, return value will be less than 0. So if the string compare of these two is less than 0, then we will keep moving. If it's the equal or greater than 0, we're going to stop. So I'm going to put this in here. I don't need that comment anymore, I think. Current is now the first player in the list with a name higher than new name. Okay, so I've just got this here, so I know that the current, I know now I'm looping through. If I go back to my images here, I've now made this loop that stops here. The trick now, though, the trick that is weird is that if we're stopping here, we need to know this one. So ZG's got a good question in there saying, shouldn't we maybe just go current next name? So if we do current next name, then we would be able to have the current pointer here, and we can say, okay, we're going to use this one as our insertion point. The only risk there is, what if we get to this node and we say current next name? So if I say this is my current and my next is null, and I try to read the name in a null, I'm going to get what's it called, a null pointer exception, or is it an error for accessing a null pointer? So there are some issues there, and we'd have to fiddle with our stopping cases and stuff like that. So yeah, Lorenzo is saying the same thing. Like, what would happen if it was that? So that's one issue. But yes, you could definitely do it that way. You just have to play around with your stopping cases to make sure you never actually get to this node. But the only problem is, what if I wanted to insert F into this? I do actually want to reach this node and then insert there. So I'm going to use a different trick for this, which might be a little bit easier, but it's got its own complications, but I'll show you how it works. What I'm going to do is I'm going to create a node that is the previous node in my list. So it's going to start off as null, because if I'm at the head of the list, there is no previous node. But then what I'm going to do is I'm going to say previous is equal to current, and then current is equal to current next. So gonna have a look at this. Okay, so let's go current is pointed at the head, And what's another color I can use? I'm kind of running out of colors. And previous is pointed at null. Then I go through my loop and I say in the loop, previous is equal to current, then current is equal to current next. So first, previous is equal to current. Current's pointing at mark, so previous is equal to current. Says previous is now pointing at mark. And current moves on to current next. So current is mark, mark's next points at ang, current becomes pointing at ang instead. So we go current moves on. What color was I using there? So what we now have is previous is pointed at the last one, current is pointed at the current one. And then if we moved on again, previous would copy current and move to ang, current would move on to chicken. So what we're now doing is moving 2 pointers along a list. So we've got the pointer that's actually testing things and the pointer that's trailing behind and going, okay, this is the one that was the one before where we were testing things. You could definitely go, okay, let's move the current along and test things ahead of ourselves. But what I'm doing is I'm testing at where I am and just trailing a pointer behind me. Because it's not going to cost me that much to trail a pointer behind me. It's just maintaining the pointer and saying, wherever I go, this thing goes to where I just was. Where I just was? Yeah. It's like, am I still speaking English or am I now speaking code? So the previous follows the current. And then the current moves on to the next thing. So current is now the first player in the list with a name higher than new name. I'm going to be specific about this here. Previous is now the last player in the list with a name lower than new name. I don't know if it's exactly lower. It might be lower than or equal to because of this. Do we keep going if they're equal? No, we only keep going. This is higher or equal. Yeah, so it's higher or equal. So obviously these are more comments than I would put in a normal piece of code, but while we're learning about things, this is kind of handy. So this is the loop through and find the insertion point. This is probably the only comment that I would have actually left in there normally, because it's like, if you read that, you could ignore all of this code and know what it was doing. So loop through and find the insertion point. So now that we've found the insertion point, insert at this insertion point. Luckily, inserting there is not too hard because we have a function that says insert after. So I can insert after my previous. So I can say insert after the previous pointer is the thing that we're going to be inserting after. And we're inserting the new name, which is the same name that we were given. Right. Perfect. Good. Done. You know, right? You know, right? If I say perfect, good, done, then you know that there's an issue. Lorenzo is saying something though. Shouldn't it be higher because we want to keep going until the second is higher? So let me see if I've done this correctly. So I'm saying keep going if new name is higher than current name. Let's go back to our thing here and say returns less than 0 if string 1 is less than string 2. So I'm going to say keep looping if this name is less than this name. So I'm saying don't stop the loop if the current name that we're seeing, so the name we're seeing is a lower name than the name we're carrying. I think this is okay because it will keep going if the current name is if the name we're seeing in the list here, so we're comparing these two, and if this is lower we keep moving. And then there's a point at which, maybe if there was a C in this list, we would move past the B and we'd stop on the C. So we're inserting I think it is the last plain list was lower, the current is higher or equal. Yeah, I think this is it. So ArtSmart asks an interesting question. What about alphabetical ordering of Matt and Mark? So we're relying on string compare to do this for us. So string compare is going to look at the M's and say you're the same. Then it's going to look at the A's and say you're the same. And then it's going to look at the R and the T. And then it's going to compare those two, and that will be the difference. Oh yeah, Michael's already answered that. Yeah, so it will go through letter by letter. We're just allowing string compare to do the hard work for us so that we don't have to. Okay, so we're going to insert after this, and we go, okay, that's fine. So let's look at the possible situations we could have here. If we're anywhere in the list and we insert after, we're probably okay. But we did have this situation where insert after could be inserting into an empty list. Insert alpha could also be working on empty lists. So if we have an empty list, the head is null and the previous is null. Insert after null is going to give us back a pointer to the new thing. So we need to deal with two situations. We need to deal with if we're inserting into a list that already has elements, or we're inserting into a list that's empty. And then when we think about this, there's one other situation we may have to think about, which we haven't really, is inserting at the head of the list. Because if we're inserting at the head of the list, we have the same kind of situation where if we're inserting after previous, and previous started as null, then we're always going to have some issues there. So if previous was null, or head was null, then we're going to try to insert into a null here. We do have code that deals with that, but we still need to be aiming at this return. Return to the head of the list if it's changed. So if the head of the list was null, we need to return the new head of the list, which was which is the new element that we've just inserted. So we're probably going to want to say, I don't know what I want to call this. I don't think that's not a good name. Maybe I'm looking at insert result here is inserting after the previous. But I have several different cases here that I might need to deal with. I might get away with treating these as the same. So if I'm inserting into an empty list or I'm inserting at the head of the list, let's try treating them as the same thing and see how this works. So inserting at the head of the list, I need to ask if I'm inserting at the head of the list. How do I know if I'm inserting at the head of the list? Let's look at the conditions here. Current's the head of the list. If previous is null, then we're in the situation where we haven't started looping yet. So if the string compare here causes us to stop immediately, or the current was null, then I know that this will never run. So previous will remain null. So I could say that if the previous is null, then I'm inserting at the head of a list. So if I'm inserting at the head of the list, I would probably do the same thing, insert, but then I would get this insert result. So what I might do is do this first. So I've got my insert result, and I've inserted after the thing. If the previous was null, then I know that my insert result is now a pointer to the element I just inserted, which means that the head of the list is now the insert result. And I know that what I'm going to do at the end is return the head. So if I'm just inserting normally somewhere into a list, this comment's probably not correct now. I'll just get rid of that and decide what I want to say about that later. So I try to insert after previous. If that insertion had been into a null, then it becomes the new head of the list. However, this doesn't necessarily tell us if there were more elements in this list or not. And what I've done is I've just replaced the head, which is probably not a great idea either. Let's draw a picture of the different possibilities of situations that we could be in. So, one situation that is reasonably easy for us to think about is, head points at null. Empty list. If I'm inserting alphabetically into an empty list, I become the only element of the list, which is, let's just say I am A. I will be pointed at null, and then the head will be pointed at me. Wrong color, but you get what I mean. Okay, so this is okay where I say if the previous was null, I'm inserting at the head of the list, and then the head will become that insert result. So that there. I have another possible situation though. What if we've got a few of these, and let's say this was named X and Y, and I insert A into this list. Now I do know that my head is definitely going to want to end up pointing here, but I also know that this connection needs to be made for me to be connected to the rest of the list. So if I just say head is equal to the insert result, I've replaced the pointer for head here. If I do that, then I'm in this position here, and I have literally lost what's in this list here because I didn't maintain connection to that. So what I need to do is, if I'm at the head of the list, I can take my insert result, which is a player, and I can say their next pointer should be equal to the head. So what I'm saying is I'm connecting to whatever's the head of the list. And this works even if it's null. So even if it's null, what I'm saying is like your next is null. It might already be null, but it doesn't matter because there's a chance that it won't be null. So what I'm saying, insert results next is equal to head. So what I did there was, let's go back to this position here. I've inserted this at the head of the list. Its next should be the head. So its next points at the same thing the head points at, and then after that I change the head to be pointed at my new head of the list, like so. It's pretty complicated, but this gets us to the example where if I insert at the start of the list or I insert at an empty list, this will work here. Because what happens is I will do my insertion and I'll get an insert result out of that. That insert result is definitely going to be the new head, but if it's the head of a list that already exists, we also need to reconnect it with the rest of the list that's there. William, good question. Surely there is a library that handles all of this code for us. Unfortunately, in C, there is no linked list library, but in many other programming languages, there are lists like this. This is actually one of the reasons why we teach C, because this depth of understanding of how to do the memory allocation, moving the pointers around and stuff like that, we consider something really useful, because when the library doesn't work for you, you have to write your own code. So in this simple case, yeah, we could probably make libraries that work for us. But when we start fiddling around with these things and trying to make custom things and stuff like that, it's really good to know how they work underneath. Yeah. So, what we've done here, let's go back through what we did. We found our insertion point by looping through and finding the point where we wanted to insert something. We then went back one pointer, in a sense, using our previous pointer here to decide where the insertion point was. Then we do our insertion. So we insert after the previous with the new name. We know that insert after is going to deal with the creation of these things, the memory allocation and stuff like that. Also, we're leaking memory in this program. We haven't done any freeing at all. We're going to do that on Friday because we don't have enough time. So the insert result is either going to just be the position we insert into, so it's going to be a copy of the previous pointer, or it's going to be something different if it had to insert at the start of the list. And so we can check that by saying, did we insert at the start of the list? If we did, we do a little bit more accounting to make sure that A, the list is still connected to the rest of it, and the head becomes the new insert result. So let's test this and see how it works here. So instead of insert after, we're going to insert alpha. So what I'm hoping for here is the head is null, and if we insert alphabetically into the head, I will just be the only element there. Then we say the head is the result of inserting chicken into the list. Chicken should now be the first element of the list, so she will be the head of the list and I will still be in the list. And we do the same thing for Ang. So what we should get is Ang first, then chicken, then me. But let's see whether this works or not. So I'm going to compile that and run it. We have Ang and then chicken, then Mark. What might be interesting is to print out in between each of these things. I'm just going to need a standard input-output library so that I can do some other stuff here. I'm just going to put some gaps in between each of these printouts so we can see the difference. No, actually, just going to copy that. So we're going to see the different steps. So I insert my name, I should be the only one in the list, and then there'll be a gap. After I insert chicken into the list, she should go first, and then me. And then Ang afterwards. Ang should also end up being the start of the list. Although, let's try to add someone in the middle of the list as well, so we're testing multiple different things. So this is inserting into an empty list. This is inserting as the head of the list. This is inserting somewhere in the middle of the list. So let's try this. Compile this and run it. So, I should have put a new line on that. Let's compile and run that again and see how it goes. Okay, so the first thing is me. And then when I inserted chicken alphabetically into the list, she came into the list before me, so she goes first. And then I add Goku to the list, and we go through the list, and it's going to go, all right, Goku's after chicken, Goku's before Mark, so we're going to insert after chicken, so Goku goes after chicken in the list, and I get pushed one along. And so now we have a way of adding elements to the list that is always going to be alphabetical, so it doesn't matter how many people I add to this list, we're always going to get an alphabetical list out of this, because the function is assuming that things are already alphabetically ordered, but they kind of are, because an empty list is alphabetically ordered, a list with only one element is alphabetically ordered, and then if we keep adding using the same function, it just keeps things in order. So yeah, that's the fiddliness of doing insertion into linked lists, as well as looping through to find an exact position there. So I'm pretty much out of time here. I will wrap up the lecture as it is now, but I'll come back in a second and answer questions if anyone has any questions and wants to know more about what's going on here and wants to maybe get me to dive into some of the code there and have a look at it and draw some more pictures and stuff like that. So I'll wrap up the lecture here. We're not actually done with this example. As I said before, we have not... did I? Oh no, I didn't put any more slides there. We haven't removed anything from the list, and we haven't dealt with freeing of memory and stuff like that. So that's going to be the third lecture in the linked list series. We're going to go into that. Okay, so I'll wrap it up there, and I'll go into break mode, and I'll come back in a second and answer any questions people have about things. Oh, hang on. Alan was asking for the live code. Oh wait, it's here. I'll copy this. And there's the link to the live code. Sorry, I should have put that in chat earlier. All right, I'm going to wrap up the lecture there. And I will come back in a second and answer any questions that anyone has. Alrighty, I am back. So we had a bit of discussion in there after I just popped out. Then, interesting things Ollie's talking about. When the program ends, it frees the memory. Yeah, so the operating system is going to claim back the memory when the program finishes running. So for our things here, it's not that big a deal because we run it and it ends straight away. However, I'm not about to just start teaching people that, like, don't worry about memory because your program's going to end and everything's going to be fine. Because we saw before that if I had a particularly aggressive memory leak in a loop, that leaking memory program that I ran was... How long did that last? Like 20 seconds? And then it was done? There's... You know, the majority of the programs that we use day to day, we're going to use them for a lot longer than 20 seconds at a time. Rare to see that aggressive a memory leak, but you get something like, I think Mike was talking about browsers, right? They're gonna be running for hours and hours and hours at a time, and you're always going to be loading new things and then removing them, loading new things and removing them. Some of those things are huge, you know, like streaming 2 hours worth of a lecture on YouTube. If you are leaking memory for every kind of few seconds of video, your computer would run out of memory very quickly. Other things like your operating system that might be on for days at a time, it's kind of bad for them to have memory leaks because they'll slow down your computer. Chrome is a very interesting example because it's not actually leaking memory, but Chrome is very aggressive with memory. So in order to make your tabs pop up really quickly, it keeps a lot of them in memory. And the raw amount of data on any particular website might be a huge amount of information. Embedded videos, ads, a whole lot of images and stuff like that. They take up a lot of space. And so Chrome says people tend to like it when Chrome's really responsive. So if they're going to keep 500 tabs open, I'm going to actually try to keep all 500 tabs in memory. And obviously your RAM just disappears when that happens. So it's not necessarily leaking at that point. It's just using all of that memory with the idea that you might want to switch to one of your 500 tabs, which in general is why I say to people, having 500 tabs open might be an issue. I like to keep mine pretty small, so I don't usually have more than about 20 tabs open at a time, but depending on the complexity of the websites you're looking at, still could use a lot of memory. Anyway, that's a little aside. I actually don't know, though. I haven't done a memory analysis on Chrome to see if it's leaking or not, but that's what I know of the general design principles behind something like Google Chrome. The Linux operating system does a lot of similar stuff like that, where, well, I actually don't know if it does nowadays, but years ago it used to do this thing where it was like, if you have RAM that you're not using, it would use it. It would be like, look, we're going to have a rough, it's really rough, prediction of the things that people might want to use, and we're going to put them into memory ahead of time. So there's a good chance that if you try to do something, or your programs move on to the next step, that it's already in memory and ready to go, as opposed to just leaving it empty and saying when you try to run something, you've got to copy it from the hard drive into the RAM and then run it, which is a slow step because the hard drive, when you think about, like, we call them orders of magnitude of speed, the hard drive is like 1,000 times slower than memory. Memory is 1,000 times slower than the registers on the CPU. So I showed you that kind of hierarchy of hardware, right? If you don't have to dip down into the slower parts of the hardware, then everything kind of runs quicker. So some things will get aggressive like that. So Chrome's getting aggressive like that and saying, with all of this stuff, I could put it onto the hard drive, and it's safe there, it's fine, and when someone asks for it, I'll grab it off the hard drive. But when you click on that tab and it takes like 2 seconds to load all that stuff from the hard drive into the memory, and then from the memory into the CPU to run it, us as humans notice. Humans are actually very reactive. We notice anything shorter than about 1/30th of a second. So anything less than that, we're like, I don't like to wait for that. Feels sluggish, you know? So sometimes those programs and operating systems will get aggressive with memory so that that tiny delay doesn't happen. It takes a lot of work to actually write operating systems to make them do that. But we kind of notice as humans, and so we like it. Like, anyone who's been using VLab from overseas, or even just on a like mildly slow internet connection, because VLab is like giving you the entire image of a screen that's rendering somewhere else. So there's always going to be lag in a system like that, and it doesn't take much for you to notice and start to be frustrated with it. So that's like one of the difficulties with us trying to provide a consistent environment to everyone through VLab, is it's very bandwidth hungry, and it triggers that kind of noticeable delay effect in humans. Okay. So William was saying that glib.h handles linked lists and stuff. So this is really funny, and I think it's really interesting that I don't often look up libraries that I'm not using, and knowing that I'm going to be teaching linked lists and teaching people how to really build them from scratch and stuff like that, I've never actually bothered to look up the libraries that would do this for us for free, because I know that, like, you know, educational goals is to get people deep into this stuff. So it's kind of like, in order to understand how this stuff works at a higher level, we must work at it at this level, and have to learn, even though there's a library that does it for you. So it's interesting. I will check out the library though, because it could be interesting. ArtSmart said something that Michael was going to pass along. Oh, the zip file in the assignment 2 pages unavailable to download. Oops. We'll deal with that. Thanks for that. Okay, so did anyone have any questions? I know that we went through... Ironically, we didn't write very much code, but it was very, very complicated code. So if anyone has any questions about the code that we wrote today, please type in questions now, and I can go back over things and look at it. I think that a lot of the time, you know, because I've taught this before, a lot of the time when we hit this lecture, or in amongst these linked list lectures, generally what happens is I show stuff. It's exceedingly complex. A lot of brains explode, and people don't necessarily have questions until after a rewatch of this, where they have to rewatch and pause it and just go, what did he actually mean by that? Let's look at this. Let's maybe draw some pictures and stuff like that and make it happen. Because it's funny, like, a function that is only, 15 lines long here, and half of those are comments. Normally we'd think about this and say, this isn't too hard, we can understand this. But when you start using pointers everywhere for everything, I think it takes a little bit more effort to figure out exactly what's going on. So, feel free to ask questions now if anyone's got any, but it looks like we've been here for a while without any questions coming up. So I'm just assuming for the moment that brains are exploding, and we're going to need to spend some time in tutorials playing around with these, working on the labs and the assignment and stuff like that, and then the questions will come up later. So maybe next week, on Friday, when this example is complete, people will want to dive more into specific things. These linked list examples are also very, very specifically similar to some of the stuff that's in the assignment as well, so hopefully this stuff will help with that. They're not exactly the same. Like, as I said, I'm never going to exactly do the assignment for you, but a lot of stuff that's similar to it might be handy. Lorenzo is saying that multi-file projects were worse than linked lists, so that's good. So I think sometimes, like, the multi-file projects is like a configuration thinking sort of things. Like, how do we piece these things apart so that humans can use them? Whereas linked list thinking is very much more abstract mathematical thinking. So maybe, Lorenzo, you've got more of you're happier with the abstract mathematical side, the problem-solving side of things. Actually, both of those are problem-solving, rather than the kind of re-engineering things for human use, which is like the multi-file project side of things. M. Stefner is saying, I wish I watched this lecture before starting on assignment 2. I was hoping that, like, the example from the first assignment, where it was like, you don't really have to start the assignment until after the first week that it's released, because tomorrow we're also doing a live stream 4 to 6 p.m. tomorrow. I'm bringing Tom in again for this one to talk about the assignment and answer any questions people have about the assignment and stuff like that. I mean, having said that, you're still, like, way ahead if you started the assignment already. I don't think that many people in the course have started the assignment, because it's been out for, am I thinking 24 hours or even less than 24 hours? The final, not the final non-draft version of the assignment has only been out for like 24 hours. So I'm really happy that you've started, actually. But you could, if you wanted to, don't do it, but if you want to, you could delete all your code and start again at this point, and you'd still have plenty of time to finish things. Blake is asking, spoiler alert, Blake, would you use these lists for stacks and queues? Huge spoiler, week 9, lecture 1, we will use these for stacks and queues. We're not necessarily going to go too deep into queues, but we're definitely I'm going to show you stacks, because stacks are such a programming thing. So we're going to talk about what stacks are, and we're going to use something like a linked list to actually implement a stack. So yes, it's coming. And I always love it when someone says, would you use this for this, or is the follow-up for this? And I was like, yes, it is, and it's in the lectures, and it's in my plan already, which means, it makes me happy, because it means that my plans for how the course goes from one thing to the next is intuitive, and it follows. Brendan's saying 100% some people have already finished it. Wow. Some people are bored. It's funny, because I haven't. I know someone, I can't remember who wrote it. I think Tom wrote the reference solution for this one, but I can't remember for certain. But yeah, I haven't actually gone through and implemented it. But I mean, I often won't implement everything that's in the course. It's like, I definitely implement, obviously, lecture code and heaps of the tutorials and labs and stuff. Actually, not all of them are mine. Only about maybe less than a quarter of the exercises in there are stuff that I wrote. But yeah, so it's interesting that people are already jumping into it, which is fun. But don't worry if you aren't jumping into it, because as M. Stefner is saying there, that maybe this would have been easier after these lectures. So after the linked list series, which ends on Friday, and also especially after the live stream on Thursday, which is specifically assignment based, a lot of people I think would wait for those two and then start on the weekend or something like that. And that actually is a fine way to start the assignment. I would say read the assignment spec before Thursday, so that when we're talking about it in the live stream, if you want to come along, you can ask questions and stuff like that. And Blake saying, yes, do they have to be doubly linked for queues? We're not specifically looking at doubly linked lists in this course. So you can if you want to, and this is if anyone's wondering. This is the concept that we could have this. So we can have pointers going back and forth between nodes. If you think about this, if we had set up a list with the pointers going back and forth, our code here would have been easier because we would never have needed to set up this previous pointer. Every node itself would have a previous pointer. Having said that, linked lists are complex enough as it is without us adding another extra thing to have to set up and modify. So all of our insertions and removals get more fiddly if we have to change multiple pointers and stuff like that. So we haven't been doing them. They can help in certain things. So if you need to go backwards through a list, it helps to do this. We're doing it with just one set of links so that we can just loop through in one direction. If we need to find something, we could start the loop again and go through. Because we kind of want to hit this at the most fundamental level rather than trying to do a more complex version of it and then ending up confusing people. So I think they're complex enough as it is with the single linkage. But if you do want to do, if you do find a reason to make a doubly linked list, so there might be some lab exercises that make it interesting to use a doubly linked list. There also might be parts of the assignment where you say, if I was to go both ways on this linked list, it might make some things easier. So you can do it. I should also point out that the entire assignment is designed without it. So we designed it, built it, did the reference solution without ever needing pointers going both directions in the list. However, if you're interested in trying it, I think it's definitely worth, I'm never gonna say to a student, that's a very interesting concept, but you shouldn't do it, right? Like, I'll never say that. I think if you find something interesting and you go, I could find a use for this, then definitely go for it, because you could learn something interesting out of it. But if you're looking at it and you say, that looks too complex, I think I'm going to make mistakes with this because it just raises the complexity level a bit, then I would say to you, go with your gut. You don't necessarily have to add these things. Also why I'm not teaching them. Yeah. Okay. Looks like we haven't got any specific questions about the code or anything like that. So I'm going to assume that everybody understands it fully and can replicate it at a moment's notice. That's mean. I don't believe that yet. I usually think that people are going to need to work through these things, which is why they're in the labs for this week and next week. And then you'll go through and you'll get more of an understanding of what's going on. Stuff is getting a little bit compressed now as we get close to the end of term, in that I know that we can't have a lab after week 10. So the week 10 lectures, I'm basically not really introducing any new content in the week 10 lectures because there's no way to reinforce it in the lab. And like week 8 has the lab, and then the lab in week 9, and then week 9 has the lab in week 10. So we're kind of running out of a lot of kind of time to do multiple exercises and stuff now that we're nearing the end of the term. So hopefully there's enough there. And there's also a week after, which is like the week 11, where people will be studying for the exam and stuff like that. I'll try to do a live stream that week as well, so that I can actually answer people's questions if people have last minute questions and stuff like that. Blake has one question about string compare. Is it just returning 1, 0, or -1, or does it return the magnitude of the difference? That's a good question, and one that I have rarely looked at, but I'm pretty sure that it will be... I'm pretty sure, but not 100% sure. I think it's like a measure of the ASCII distance between them. Having said that, let me throw this back to you, Blake, to try out. Because this should actually not be a super difficult piece of code to write, where you could say, like this example code here with 2 strings, and the cases as actually, because string compare is using ASCII values, so it will actually say that lowercase, I think, is earlier in the alphabet than uppercase. I have to look at the ASCII table to see that. If you want to, you can do the string compare, get that to go into an integer and print out that integer and say these 2 strings are this far apart, and try punching in a lot of different strings and seeing what the difference is. Because I don't think you can just get a number out of this, because if you got a number, you could measure the ASCII distance between 2 characters as a number. But between 2 strings, it's kind of like, is the first letter more significant than the second letter? And if it is more significant, should it have a different value or something? So it's really hard to say what that number should be. But I think this would be a cool one. So if you want to create some code that actually records that number and sees what the difference is and print it out, and see if you're getting anything beyond just a 1 or a 0, or if you're getting literal ASCII distances between things, because I think that might be interesting to look at. I haven't done it because I tend to just use it as a more of a yes/no thing than a specific distance between things. All right, I might wrap it up there. Blake, please let me know how you go with that. Maybe tomorrow's stream or Friday's lecture, you can let us know how string compare works, because Friday's lecture we're going to use string compare again, so that would be a good time to say, well, oh right, you've just done it there with A and Z and it returned -1, so it's actually only giving you a difference between things. Or try it with longer things than A and Z, like AAA and ZZZ, or AAA and AAZ, and see if it has to go further into characters if it returns something other than -1. I'd be interested to see that. I mean, actually, the time I've spent talking about this, I could have written the same code that you have. But I thought, you know, as a teacher, you try to convince your students to do the investigating because it's more valuable for you. Oh, okay. So it's really only giving us a -1 or a +1. Okay, so it's not measuring distance. It's just measuring if there is a difference rather than how far that difference is. Good to know. Interesting to learn these things. Okay, I'm going to wrap it up there. Thank you, everyone. Hopefully the linked lists and multi-file projects and stuff like that aren't breaking people's brains too much. And you'll have plenty of time to get acquainted with these over the course of the second assignment anyway. All right. See you all tomorrow if you're coming tomorrow to the assignment live stream. Otherwise, Friday for the lecture then. Catch you.